All right, it's Friday, guys. Friday. Let's go ahead and get started here on parallel axis theorem. We've got a long ways. I just remembered that I cut off a day for circular, but it looks okay. It looks like we can make it through. Just doing it 5 days because originally it's 6 days that I cover circular motion in, but it looks like we're going to be able to finish it in 5. So we should be done next Wednesday. And the homework for this, I just opened it up this morning, just a while ago, about 5-10 minutes ago. So that's available now. You guys need to start on that homework. And it'll be due next Thursday. Or Wednesday, sorry. We'll be due on Wednesday. You should be able to do the first problem or two. So if you just do a problem at a time, you should be good to go. All right. Parallel axis theorem. So earlier on Wednesday, we talked about the moment of inertia, all right? And we defined all those moments of inertia based on an axis that goes to the center of an object, right? So we're going through the center of a rod, either vertically or horizontally to the center of the rod, or through a sphere, going through the center of a sphere, something like that. But sometimes we don't spin things through the centers of objects, right? Sometimes we spin things through some place that's not the center, something that's off the center like this. So we'll spin this thing, like my stylus, around this point here, right? Yeah, that's the best example I can come up with, right? So we have to figure out then how to find the moment of inertia about this point instead of through the center. We want it about this point. All right. And so that's where the parallel axis theorem comes in. We're able to make an axis that is parallel to the one going through the center, right? We have an axis going through the center here. And so I can make another axis going through this point here that's parallel to the one going to the center. And then I can use some math to figure out what the moment of inertia is about here. All right, so that's what we're going to do. So parallel axis theorem. If an object's center of rotation right? So remember that center of rotation means the center that it's rotating about. So here, the center of rotation would be right here where my fingers are, not the center of mass, not the center of gravity. It'd be over here, center of rotation, the point that it's rotating around, okay? So if an object's center of rotation is not through the center of mass, then we can use this parallel axis theorem to calculate moment of inertia. All right, and the equation for that is I is equal to, so remember that I is moment of inertia, and it's going to be equal to the moment of inertia about the center plus the mass times a constant k squared. Right, so IC again, IC is moment of inertia at the center of mass right? And we can get that from that table that I showed you guys before, which I forgot to send you guys. I'll send that to you. I apologize for that. I'll send that to you guys because you guys are going to need that for your homework if I remember correctly. M is mass. And then K is the one that we don't know what that is. We don't know what that's called. So first, don't get this confused with the K that we used for the spring constant, right? This is a different K. All right. So again, there's another variable in there that uses the same letter as we use for something else. But I mean, it's the same idea as with the English language, right? For example, the word well, right? I'm feeling well today. It means that I'm feeling okay, right? I'm feeling good. Or I could say, go get water from the well. Well, now you understand that it's a hole in the ground that has water that I'm supposed to bring up with a bucket. So depending on the context of the problem, depending on the context of my language, you guys know what I'm talking about. You know which definition I mean for the word well. It's the same thing here for physics. Depending on the context of what we're looking at, we need to figure out what the K means. In this case, the K means the radius of gyration. And you don't know what that means either, so I'm going to explain it to you. The radius of gyration is just the distance. Let me move this guy down. The radius of gyration is a distance, okay? And it is a distance between the axis of rotation right, and the center of mass. All right, so again, taking my stylus, let's say this is the center of mass right here, this point right here, and I'm spinning it. This is the axis of rotation here. The distance between those 2 points, the center of mass and the axis of rotation, is going to be my K value. Okay, it's just that distance. How far away is it from the center of mass? That's what I'm asking. That's what K is. All right, so center of mass here. And over here, I'll say this is my axis of rotation. Right, so the distance between those two is my K. All right, that's it. That's K. And again, you need to consider the context of what the K of the problem to understand what the K is, whether to know it's for the spring constant or whether or no it's the radius of gyration. If we have this rod is spinning about this point, then you're talking about K, the radius of gyration. If we're saying the spring is being compressed this much, K is equal to something, then we're talking about the spring constant, right? Consider the context of the problem. All right. So what we're going to do is in our moment of inertia, we saw this guy here, where we had a thin rod with the axis going about its center, and then we had a rod with the axis going about the very end of it, right? This is where it's rotating at the end of the rod like this, right? So this is the end of the rod. So we're talking about this. We're going to derive this equation based off of the center of mass equation here. Okay, so that's what we're going to do, just so you can get an example and compare it and see how we do that. So going here, let me move this down again. I didn't want to delete these things because it's a pain to draw these things out. So that's what we're going to do. We're going to derive inertia for a rod. Rotating about one end. All right, so that's what we're doing here in this next little bit. Okay, so again, we've got our center of mass. It's going to be right here. This is the center of mass. Okay, And we're going to set our axis of rotation here at the very end of the rod. All right. We're going to have a total distance for the rod L. And so for the center of mass, then the distance from the center of mass to this point to the axis of rotation is going to be K is equal to is L over 2. Right. So K is equal to L over 2. Okay. So let's write down our equation. I is equal to IC plus MK squared. All right, and I'm just going to plug this stuff in. IC from our table, let's go back to our table to see what IC is. The center of mass is ml squared over 12. Again, it doesn't matter lowercase or uppercase. It's not too important in this example. So ml squared over 12. M is just going to be the mass. We're going to leave that as is because we're looking for a general equation, something that we can use for any situation. And then K is equal to L over 2. All right. So I'm going to plug those into our equation. We're going to have I is equal to ml squared over 12 plus m times L over 2 squared. And that's just, all right. That's going to give me ml squared over 12 plus ml squared over 4. Right. So these denominators need to match, right? Of course. So we're going to leave the first one alone. I is equal to ml squared over 12. The second one becomes a 12 on the denominator, and so we have to multiply the top by 3. So we have 3 ml squared. That's going to give us 1 12th ml squared plus 3/12 ml squared, because ml squared gives us 4 over 12 ml squared. Right, and so then we can just reduce that to 1/3 times ml squared. Right, so from the parallel axis theorem, we can get our moment of inertia if the rod is spinning on one end of it, right? Where L is going to be the total distance of your rod, M is the mass of the rod, and that gives you your moment of inertia. And again, it's going to be kilogram times meter squared, right? That's the units for a moment of inertia. Get this example. I'll give you a second to write it down. While I go get some water. I forgot to grab water. All right, so calculate the inertia of a 0.56 kilogram meter stick. All right, so I'm going to write down that the mass is 0.56 kilograms. Stick about an axis perpendicular to the stick and located at the 20 centimeter mark. So the distance from here to here, this is where I'm going to put my axis of rotation, is 0.2 meters. And it's going to be too small for me to write, so it's 0.2 meters there. Okay. Got M. I'm trying to find the moment of inertia. So I need to figure out K, right? K is the distance between here and here. So I need to figure out that K first, right? So this is a 1 meter stick, right? This is a meter stick. So the distance from here to the end of it is 1 meter. Right? So that means the distance from here to here, oops, too far, to here is 0.5 meters. Okay. So this bit plus this bit gives me 0.5, right? So I just need to subtract 0.2 from 0.5. That gives me 0.3 meters. Okay. And again, I have a mass of 0.56. Just going to write it down here so I don't have to keep scrolling up. And the total length L is 1 meter. This is a meter stick, so it's 1 meter. All right, so I've got everything I need here except for IC. Sorry, it's plus mk squared plus mk squared. But we already know IC from last time. That's going to be ml squared over 12. Okay, so I'm going to go ahead and plug in the values for IC. That's going to be 0.56 for m, 1 squared over 12. So it's going to give me, let's see if I got it written down, 0.047 kilogram meter squared, right? So I can plug in that value directly into my equation now. So I is equal to 0.047 plus the mass is 0.56 times that K was 0.3, so it's going to be 0.3 squared. So I is going to be 0.097 kilogram meter squared. Now, we have time to do this, so I'm going to go ahead and do this. It doesn't have to be, well, hold on. Let me make sure that's true. Let me do it real quick on paper. I want to do this. I want to do this with you guys to show you something. So if it works out, I just need to make sure my math is correct real quick. This was no, I don't think it works the way I think it was going to. So never mind. We're gonna skip that because I'm not sure I'm not 100% sure that works out. But all right, so let's skip that. But I can show let's show that it is, you do have to use the center of mass, I. So if we were to do this, let's put a, let's show that if, what if we used the other equation? What if we used this equation to figure it out? I can tell you I don't think it's going to work. So all right, so let's say we use the other equation. So I not C plus mk squared. All right, and so let's use the other one. So that means that if we use this equation, I know I is going to be 1/3 ml squared, and then my k value would be 0.2. Okay, so and everything else stays the same. But we can go ahead and substitute those values. So it's going to be 0.56 times 1 squared plus 0.56 times that 0.2 squared, and that should not work. 0.56 divided by 3 plus 0.56 times 0.2 squared. I got, you guys tell me if you got the same thing, because this is the first time I'm doing this. So 0.209 kilogram meter squared. So that's not right. This is the correct answer. So just keep in mind, it has to be the center of mass. It has to be the moment of inertia about the center of mass. All right, that's what that C stands for, center of mass. So just make sure, you're paying attention to that, I guess is what my point is.
So the 0.3 that we used is just the distance from the center to the 20 centimeter mark.
Yes.
Okay.
Yep. Torque, not twerk, torque. Torque is a moment of a force. It's the result of applying a force to cause rotation, right? That's the point. So, so like a wrench, and that's the traditional classic example that we give. So, torque is the cross product of the lever arm. Can you guys believe it got to 99 yesterday?
It was pretty bad.
I'm already sweating over here in my room with air conditioning. The cross product of the lever arm and net force. I get really grumpy in the summer because it's so hot. I get real grumpy. The lever arm is the distance from the center of rotation of a body to the net force. And I'll show you what that looks like. All right. So let's say again, we're screwing on a nut on a bolt. Okay. So here's our nut. Okay. Here's a hole with a nut. All right. Now we've got this wrench that we're going to use. See if I can draw it as well as I did have it in my notes. All right, so there's our wrench. Okay, and I'm going to apply a force right at the end of this thing to twist that nut, right? Actually, I'm loosening it. I'm loosening it if I'm going that way. All right, so I'm trying to loosen it. And so I'm applying that force right at this point. And then the center of rotation is going to be right in the center of this bolt, right there. All right. The distance from the center of that bolt to where I'm applying my force, F, that's my lever arm. All right. So we can call that R, but that's the lever arm. Okay. And so now that we understand what that is, the torque then, and so we use the Greek in this class, we use the Greek letter tau. Okay, that's the Greek letter tau. Tau is equal to R cross the sum of the forces. Right, and so we can expand that. We can include our position because sometimes the forces might have a different position. We might have another force acting over here or something like that. So R is going to change, and so you have to match the R with the appropriate force. So it'd be R1 with F1, R2 with F2, and so on. So that means that we would have to sum the positions in here as well. So it'd be R cross F. So the sum of the total of that. Sum of all of these, all of those things. Okay, so that's our equation. We can take it down to a scalar, which we'll do in a little bit. The units are the Newton meter. All right. And the direction of the torque is found using the right-hand rule. And what that direction tells you is where the axis is that the object's spinning around. Okay, that's what the direction tells you. Where is the axis that what direction is the axis going that the object is spinning around? Which in 2 dimensions is very obvious, right? In 2 dimensions, the axis that this nut is spinning about is going to come out of the page, right? My right-hand rule, see if I can show this on here. My right-hand rule, right, is I put my thumb, I put my thumb right at the center of the rotation, okay? So my thumb will go here, and my fingers are going to go in the direction that the force is going in, right? So my force is going up, so my fingers need to go up. And so the direction that my thumb is pointing in is going to be the direction that my axis is going in. So in this case, for this example, my thumb is pointing out of the page. That's positive. So it's going to be a positive torque. And so the axis is coming up straight out. The positive direction of the axis is coming straight out this way. All right, so So mathematically, we've talked about what torque is, but more practically, torque is just a twisting force that causes rotation. All right, that's all it is. It makes rotation. It makes something rotate. It's a force acting at some distance from the center of rotation that makes it rotate from some distance. All right. All right, so let's simplify this idea a little bit. Let's say that's our origin. That's the center of rotation, that O. And we're applying a force right over here, F. Right, so this is R. This is my lever arm. And I'm going to extend this out in the direction of the force and the position. And we're going to look at my equation. Let me drink some water. Okay, we already talked about this, that torque is equal to R cross F. And we know that the cross product of the cross product is going to be R times F times sine of theta times, some, the direction in hat. That might be I hat, J hat, K hat. It might be some combination of those things. So we'll just put in hat. Okay. So this angle here, the angle that we're talking about in this case, is going to be the angle between R and F. All right. So we're talking about this angle here. This is our theta here. I'm going to extend the lever arm, the R position out, and like it's kind of like we call it a line of action. So we're going to make the line of action because it's acting along that whole line, right? R is acting all along this little, I guess, axis type of deal, right? And F is acting all along this imaginary line here. Okay, so we call that the line of action. It's acting there, right? So the position vector, I'm going to extend the line of action out to the right, and I'm going to extend the line of action for my force upwards. And then the angle that those two make here, that's the theta that I'm talking about. That's the theta that I want. Okay, that's the angle that I care about. When theta is 90 degrees, then sine of 90 is 1. And so tau just becomes, we can drop the vector, then tau just becomes R times F. Okay. And I want to note something at this point then, that let's say that my force is coming out this way. Instead of straight up at a 90-degree angle, it's coming up this way, right? So my force is made up of the X and Y component. So we've got the Y component coming this way. And we've got the X component coming this way. All right. And of course, we have R. Now, here's the thing. If I push with F of X on that point, is that going to cause a rotation of that point about the center O here? Right? If I'm pushing with a force here, if I want to cause this thing to rotate, and I'm pushing directly this way, is it going to cause a rotation? Okay, thank you. No, it's not. Okay, but this one will, right? The y component of that force will, the y component will cause my stylus to rotate. Okay, so something to remember is that the forces, only forces that are perpendicular to my lever arm are going to cause rotation. Forces that are parallel to my lever arm are not going to cause rotation, right? This is not going to cause a rotation, but this one that's acting perpendicular to my lever arm, that's going to cause rotation. Okay. So only the component of a force that is perpendicular to R is going to contribute to torque. All right, so in this case, only Fy would contribute to my torque in this case. Fx will do nothing. Why? Because it's at 0 degrees from R. The sine of 0 is 0, so there's no torque caused from f of x. But this one's at 90-degree angle. Really, I should do it this way. It's at a 90-degree angle there. So it will cause a torque. All right. So just remember that Fx is parallel to R, so it's causing no torque. Fy is perpendicular to R, so it's the only one of the components that is contributing to my torque. All right, and we do have a secondary definition of torque that we're going to talk about real quick. Secondary definition of torque. And it comes to the same thing though, all right? So our secondary definition is going to be that tau is equal to L times F, all right? So R is specifically, right? R is specifically from the origin of rotation, from the center of rotation to the point where my F is being applied. L is something else that we can play with, and depending on the situation, we'll want to use one or the other. So this is, again, this is my origin, this is my force F. Let's put this at an angle, actually. All right, so this is R. Okay, I'm going to extend the line of action of F. All right, so I'm just going to draw an imaginary line that goes out from F, that F acts on. Okay, I can draw another line that goes from O and is perpendicular to this line of action. That line is L, right? So if I can use geometry to figure out L, then I can just use that distance L times my force F, and I have my torque. Okay, so just label this again. This is the line of action. Line of action. All right, the line of action is just an invisible line that extends out from the force or whatever you're dealing with. So the force can act anywhere along that line. And L again is just the distance from the center of rotation to the line of action, not to the force, but to the line of action, a perpendicular line to the line of action. Okay. And that can be useful depending on the situation. Let's just write this down, definition out. This is L is perpendicular distance from the center of rotation to the line of action. okay? Of F, I should say, of F. So we're clear about the line of action of what? Of F, the line of action of F, okay? All right, example 7. We're not getting as far as I was hoping. All right, let's see how far we can get in this example. So the length of a bicycle pedal arm is 0.15 meters. All right, so a downward force of 100 newtons is applied to the pedal by the rider. So we've got a person riding a bike, and the distance from where his foot is on the pedal to to the center of rotation is 0.15 meters, and he's applying a 100 Newton force. What is the magnitude of the torque about the pedal arm's pivot when the arm is set at an angle of 30 degrees, 90 degrees, or 180 degrees? All right, so let's do this. A. All right, so the first thing I want to do is I want to draw a diagram. So here's my center of rotation O, right? That's the point where my bicycle pedal arm is attached to the gears or whatever, okay? Up here, this is my pedal, right? And it says that the rider is applying a 100 Newton force down, right there. It also says that this pedal arm length R is 0.15 meters. Okay. So in this case, the easiest thing to do is I can do a couple things. I can figure out what the components of the 100 Newton force are relative to the direction of my pedal arm. Okay, so I could figure out this. I would figure out that component and that component, but that's very difficult to visualize. Okay, or not visual, but it takes some practice. It's not difficult, but it takes some practice to do, right? So the other option that I have, instead of using tau equals to R times F, I can use tau equals to length times the force. So I can extend the line of action out from there, from my force, and I can figure out L based on geometry here. Oops. I can figure out L. Let me do that. Okay, and so then I can use that tau is equal to L times F. Okay, that's a lot easier. The math is going to be easier. It says what is the magnitude of the torque about the pedal arm's pivot when the arm is at an angle of 30 degrees? So we're looking at this angle here in this case. Right, so I can use some math, right? I can use some trigonometry to figure out what L is. In this case, L is going to be cosine of 30 degrees. So L is going to equal to 0.15 times the cosine of 30 degrees for A. That's going to give me 0.13 meters. So tau is going to equal to 0.13 times the force of 100 newtons. So tau is just 13 Newton meters. And so just to say it again, I don't want to use tau equals to r times f in this case. I could, but the problem is a little bit more difficult for R to do that because I'd have to figure out the angles and do a whole lot more geometry to figure out what the components of this 100 Newton force are. I'd have to set I would have had to set my my coordinate axis along R and figure out those angles there based off this angle here. And so there's some more geometry going on there than I want to do whenever I can simplify this by extending that line of action and figuring out L. I would have had to do a couple of different trig functions over here. Had to figure out exactly what this angle, oops. I would have had to figure out exactly what this angle here is. And there's some more geometry stuff that, it's more complicated than it needs to be. So we use tau equals to L times F instead of R times F to simplify things. What happens whenever B is 90 degrees? Or whenever theta is 90 degrees? All right, so we should already know what's going to happen, but we're going to have L is equal to 0.15 times cosine of 90 degrees. Yeah, so tau is equal to 0. There's not going to be any torque, right? If, just to draw that out, that's O. My pedal's up here now. I'm applying my 100 Newton force straight down along that pedal. You know, we've got this 90-degree angle here. That force is not going to cause this thing to rotate at that point. Okay, because the force is acting along the length of the pedal. Okay, so that's not going to cause a torque. That's not going to cause a rotation. So the torque there is going to be 0. And finally, C, we've got a couple more minutes, so we're good. What happens if it's 180 degrees? Right, so now this is O. Now this angle here is 180 degrees. So my pedal's this way. My force is being applied here at this end. So this is 90 degrees. So now it does make sense to use R times F, right? Where this distance is 0.15. Because my force is exactly 90 degrees to my pedal arm. Right, so that's just going to be 0.15 times 100 newtons. So that's going to give me 15 Newton meters. Right, so you have to think about the situation and see which one of those two options for our torque is going to work best for it. All right, we're out of time. Hopefully everyone understood what's going on today. I'll have this video up this afternoon, so you can go back and look at that. And I also forgot to do the video from Wednesday. I forgot to upload that. I uploaded that this morning as well. So that should be up. This one should be up later this afternoon, if not in a little bit. So we'll see you guys on Monday. Have a great weekend. And as always, if you have any questions, feel free to email me and I'll respond as soon as I'm able.
Thank you, sir.
Thank you, sir.
Great.
Bye, sir.
Bye, guys. Bye, everybody.